Welcome to another episode of Progress, Potential, and Possibilities, discussions with fascinating people designing a better tomorrow for all of us. I'm your host, Ira Pastor.
Welcome, everybody, again to another episode of our show. Today, bringing you another really awesome guest involved in research, creating a better tomorrow for all of us. Today, we have the honor of being joined by Dr. Christopher Stubbs, Samuel C. Monker Professor of Physics and Astronomy, as well as recent Dean of Science in the Faculty of Arts and Sciences, Harvard University. Dr. Stubbs is an experimental physicist who's been working at the interface between particle physics, cosmology, gravitation, and he has wide-ranging interests, including experimental tests, the foundations of gravitational physics, searching for dark matter, characterizing dark energy, as well as observational cosmology. And he was was a member of one of the two teams that ultimately first discovered dark energy. He is heavily engaged and interested in big projects, such as the construction of the Large Synoptic Survey Telescope. He's one of the inaugural project scientists there, also founding the Apollo collaboration that used the lunar laser ranging to ultimately probe for these interesting gravitational effects. He received his International Baccalaureate from Tehran International School back in 1975, went on to do a bachelor's in physics, University of Virginia, and then a Ph.D., University of Washington, a recipient of numerous awards and fellowships. He is also an Annenberg Distinguished Visiting Fellow at the Hoover Institute, and he has also served as a member of the Jason Advisory Board, this really elite group of scientists that provide technical advice to various government agencies on national security issues. And he's got a new book, Going Big: A Scientist's Guide to Large Projects and Collaborations, ultimately which sums up all the really important critical skills that scientists need to make transition into these really important large projects. Honored to have him with us. A lot to get into today. Dr. Christopher Stubbs, thank you so much for taking time to come on the show.
My pleasure, Ira. Thanks for having me.
Yeah, no, it's awesome having you. These are topics that we don't normally get into. Really excited about them. Would love to start off by handing you the floor for a little bit. If you could, we haven't had too many guests that sort of started their journey off in Iran, but if you could take us a little bit on your early journey from Iran to Virginia to Washington, and a little bit about what got you interested in, take us up to 1988 and doing your dissertation on this search for a fifth force amongst the standard model. I would love to hear a little bit about this background. Sounds awesome.
Okay, well, that's going back a while. My father was in the Foreign Service, posted to Vietnam. We lived as a family in Vietnam, and when the U.S. entered that war militarily, all dependents were evacuated. So me, my brother, and my kid brother evacuated first to Bangkok, then to Hong Kong, eventually ended up in Northern Virginia, where my mother was working while my father worked for the propaganda arm of the U.S. government in Vietnam. And their marriage was a small casualty of the Vietnam War. So they were divorced. And my mother decided we'd have a better quality of life abroad than in the U.S. And she moved to Iran to be a school teacher. So she actually taught at the high school that I attended, which was a sort of international baccalaureate high school, essentially the high school for the kids of diplomats in Tehran, in a nutshell. The language of instruction was English, but the language on the playground was Farsi. So I became fluent in Farsi. I have a high school diploma for all the good it does me in my chosen profession. And one of the great strengths of that high school system is we had 3 years of physics in high school. So I started physics in 10th grade. And about 2 or 3 weeks into my very first physics class, I thought, man, this is just the way my head is wired. This is just so rational. I love this way of thinking about the world. And this is just matches who I am in a really sort of deep-seated satisfaction sort of way. And there I was, 12th grade in Iran, trying to figure out where in the US to apply to go to university because I was born in Germany when my mother was English. And if I didn't reside continuously in the US for some number of years between some ages, I would lose my American citizenship. So going to university in the US was like the only option for me. And my father at the time was posted to the State Department in DC and was a resident of the state of Virginia. So I applied to the University of Virginia as a sort of in-state student, listing his Virginia address as my domicile. Went to the University of Virginia as an undergrad. I was lucky that a distant relative of mine was actually on the physics faculty. I had a nearly terminal case of culture shock moving to Virginia at age 17 from the Middle East. And speaking, unaccented, neutral North American English, people thought I was a native, but I in fact was not. So that was a whole interesting, traumatic early life experience. But my dad and this distant cousin got me through that and ended up as an undergraduate working a lot in a laboratory that did experimental gravitational physics. And I think that really set the course of my professional career after that. Went to Seattle to go to grad school. And while I was there, a sort of eruption of interest in the idea that there might be some aspect of gravity that didn't quite work the way that we thought. And there were a couple of pieces of evidence that pointed in the direction of some funky extra interaction with an effective range of a few kilometers. And that sort of explained a bunch of anomalous experimental results at the time. And there was no refuting counter data, right? So we embarked on a project to test that hypothesis. It was called the fifth force at the time, kind of had a lot of notoriety. It got a lot of attention in the physics community because that was a pretty unexpected, out of left field idea. And had a great time. I feel really privileged to have worked in a super competent team of people, a really tight-knit, hardworking group. We pushed really hard, and within a year, we had driven a stake through the heart of that idea, and I think had generated experimental data that pretty firmly excluded that possibility. And that earned me my PhD, and things went on from there.
Awesome. Awesome. Yeah, and following that, you begin working quite a bit and publishing rather extensively on the search for dark matter. I had, as you know, Artie Garg, who was one of your students and did her PhD under you, was on the show a couple months ago and talked a little bit about her dissertation. The program, or I guess it characterizes the Macho project or Super Macho project. You sort of sum up in this piece in 1999, Baryonic Dark Matter, the results from the microlensing project. Would love to get your sort of perspective on that project. But as we're going to be getting into sort of talking about big projects, and while I was not able to sort of pull down sort of the full data around that, I assume sort of that was your first foray into, hey, this is a good way. We learned some things. We learned how to do and not to do large projects, large collaborative projects of this nature. Talk a little bit about that as well, if you would, because, and again, we'll be getting into stuff in the book, but if you can take us back to the Macho days and talk a little bit about some of your learnings from then as well, that'd be important.
So when I finished my PhD, in retrospect, it's kind of hard to believe I had the audacity to do what I'm about to describe. But I sort of looked around and asked myself, what's the most interesting remaining open question in fundamental physics, and where can I go to work on it? And I had heard an incredibly influential talk for me by Michael Turner of the University of Chicago when I was a graduate student, who walked in and said, we don't know what most of the mass in the Milky Way is made of. And he explained this whole dark matter problem, which is that You can measure indirectly the mass of a galaxy by measuring how fast it's rotating. And if you use that mass estimate and compare it to all the stars and gas, there's like a factor of 10 difference. That's not a small thing. So 90% of the mass of galaxies like the Milky Way, we have no idea what it is. That's the dark matter problem. And at the time, the hotbed for research on dark matter was the University of California at Berkeley. And I essentially talked myself into getting a postdoctoral research appointment there to go chase dark matter. Started building laboratory cryogenic detectors to look for particle dark matter scattering off detectors in the lab. And while I was there, Charles Alcock of Lawrence Livermore Lab gave a talk where he basically said, there's an alternative dark matter hypothesis, which is that there are great big compact lumps of astronomical stuff out there floating in the galaxy. And the way you can detect it is by using the one thing about dark matter that we know for sure, and that is that it exerts a gravitational influence on things around it. And so if these things are out there floating around, they could be black holes, they could be failed planets, who knows? Just some massive compact halo object. Every so often, one of them would pass close to the line of sight to a distant star and actually act like a time variable gravitational lens. And just like if you put a magnifying glass in front of a flashlight and move it across, the thing that you look at gets brighter and then fainter again. And that's a really distinctive signature. So I went into my boss at the time, and I was a laboratory experimental physicist, remember, right? And I said, that's a really cool project to go and measure the brightnesses of 10 million stars and see if you see this effect. And my boss at the time, Bernard Satoulet, who I totally credit with giving me the intellectual latitude to do this, said, who of us is going to drop what they're doing and go work on an astronomy project with a telescope? And I said, boss, if you let me do it, I'll do it. So I shifted, a year after getting my PhD into making measurements with telescopes and looking for this signature of dark matter. And that led to this Macho project. The word Macho is a play on the word WIMP, weakly interacting massive particle, which was at the time the favored particle physics candidate. So a friend of mine sent a tongue-in-cheek email, said, well, we should call these lumps of astronomical stuff machos, and that just stuck, right? So us and a bunch of other teams embarked on big astronomical survey projects to measure the brightnesses of 10 million stars, which at the time was a really computer-intensive, data-demanding, ambitious project. I think most of the astronomical community thought we would fail in trying to do this, but about three teams embarked on doing this, and I think that produced some of the most stringent results on what the dark matter is not. Those projects did not find evidence for machos in the halo of the Milky Way, and over a wide range of possible masses excluded that as a possibility.
And a couple years after Macho wraps up, you're involved in producing this book. It's a book-sized report from National Academies entitled "Astronomy and Astrophysics in the New Millennium." It's published in 2001, and in this book, you and a very distinguished panel talk about these pressing scientific questions that were still out there, including what you were just describing, and then go into a lot of the themes that you get into the book. That we're not just going to learn important scientific stuff here, but this science has an important impact on the general public's imagination, our education system, our national life. Talk a little bit about big projects. I mean, you define them in the book as projects that require extraordinary investments of time, labor, funds, and passion, all of obviously which you had going into these, and you give examples of such as the James Webb Telescope, over budgeted, Human Genome Project under budget, and some that got canceled, like the superconducting super collider. Talk about big projects. Talk about why we require them still in 2025, and why it's not good enough just for scientists to hang out at the bench.
Yeah, so the process you described at the beginning of that is called the Decadal Survey of Astronomy and Astrophysics. And the astronomy community sort of gets together every 10 years and lays out a roadmap of here's the current snapshot of the state of the science. Here are the most pressing open questions on which we can make some forward progress. And importantly, here's a rank ordered, prioritized list of the facilities that the community consensus thinks are the right investment for the future. And that is a super powerful process that the astronomy community goes through because those decadal reports really are a consensus viewpoint of a broad community. And I think astronomers are fortunate that people really do sort of rally around that because they have faith in the process. It may be that your individual project wasn't ranked first, but at least you lost in a fair fight among colleagues and you just didn't make your case as persuasively as other people did for alternative things to do. So the science agencies that fund that basic science research, the Department of Energy, the National Science Foundation, and NASA predominantly for our field, really do pay attention to that decadal survey as they make investments of taxpayer dollars. It really does guide the national investment strategy. And astronomy in particular is not an experimental science, it's an observational science. It's sort of a passive aggressive way of doing science. All we can do is soak up the radiation that lands on the Earth from the sky, and from that infer properties of objects and the nature of the universe that we inhabit. That makes it different from physics because, at least in a physics experiment, if you think there's some funky contribution to making an error in your measurement, you can go into the apparatus and tweak the temperature, change the voltage, change the flux, and then see what happens, right? You can like change the apparatus and measure what happens as a result. In astronomy, we can't so much do that. It really is a big difference. And astronomy hinges on access to increasingly capable sets of national facilities or institutional facilities at universities. And I think in many fields of science, as the intellectual frontier involves measurements and experiments that are increasingly difficult and challenging, you sort of see and a consolidation into fewer larger projects. The Human Genome Project is an example of that, right? Where, big ambitious goal, let's go map the genome of an individual person. And that you can see has led now to where the sequencing of human genes now is way cheaper than it was when they first did that. That technology is moving really fast. But at the early stages, that was a hugely ambitious, let's get everybody together, spend a lot of money, build a big collaboration, and get something done. And in the dark matter detection game now, where there used to be a dozen mom and pop dark matter detection experiments, as the frontier moves to be harder and harder and harder, it sort of consolidates into fewer larger projects. So that requires an interesting transition in scientists where the graduate education of a typical scientist is an apprenticeship program at the elbow of some more senior scientist working on some project. And that often happens in a sort of smallish group environment. But how do you train people to then be an effective participant in a project where the number of authors on the paper can be measured in the hundreds or thousands? And they're a small part of a really big endeavor. That's an interesting professional transition. How do you find your niche? How do you make a mark for yourself? And I felt like there was a gap in professional preparation for people. And in having myself kind of gone through this transition of PhD in a group of 5 people, postdoc doing experiments with a dozen people, moving up to increasingly larger projects, now culminating in the project that's on the screen behind me, which is $1 billion ground-based telescope to go scan the whole sky and do time-lapse photography of the solar system, the galaxy, and the universe. That's a big thing, right? It's taken 20 years to build it. It's taken hundreds to thousands of people. It's, ballpark round numbers, $1 billion investment. That's a big thing. And teaching scientists to be effective where there's now a lot of project management, there's a lot of budget control, there's a lot of formalism. How do you even equip scientists with the vocabulary to talk to a technical project manager in a meaningful way. And, I think in some ways, an encapsulation of the challenge that we face is scientists pushing for improved performance and project managers trying to deliver something on budget and on schedule. And how do you balance those tensions against each other to get to a sweet spot in the outcome?
Um, Chris, I want to ask about two. Well, one was a paper in the International Journal of Modern Physics. This was 2007, entitled "Addressing the Crisis in Fundamental Physics." And then a couple of years later, you gave a presentation at Brookhaven entitled "Dark Energy: A Crisis in Fundamental Physics." And sort of the dark energy problem was the theme in both of them. And the word crisis popped out at me because as we're chatting before the show, I'm a life sciences guy. Sort of grew up in the pharmaceutical industry, and our industry has its crises. We it's 2025, and we have a crisis in terms of progression free survival and for most solid tumors, and in the oncology space we got this antimicrobial resistance issue that no one's addressing because we're not developing a lot of new antibiotics. Things like that are the crises that we find in life sciences. When it comes to crises in physics, obviously, point out the dark energy problem is one of them. Maybe I spend a little too much time on YouTube, but there seems to be a lot of sort of physics influencers nowadays that say there's crises all over the world of physics. Mostly has to do with sort of theories of everything, and somebody shouting that string theory is better than quantum loop gravity and all this other stuff that I'm not even going to try to get into. What are the fundamental problem of crises in physics as we sit here in 2025? I guess dark energy is still part of that, but if you could take us through a little bit of that, and then I'll bring this back together in a unified area.
Yeah, so I think different people are going to answer your question somewhat differently. We talked about dark matter, which is most of the mass in the universe is not stuff in the periodic table, and we have no idea what it is, right? Separately, there's a different problem that we call the dark energy problem that I think many people, including me, think is in some ways more fundamental and more interesting. And it's the following, and that is a pair of teams of astronomers went out to measure the change in the rate of expansion of the universe over time. And universe is expanding. We've known that since the 20s. And the question is, okay, so is that slowing down? Because if the universe was really, really dense, that expansion rate would eventually slow down and the universe would recollapse. If the universe is really sort of not dense, that expansion would just continue for a long time. The real big surprise was when we went out to measure how fast is the universe expanding as you look back in time, the answer, which at this point is really quite secure from a lot of different lines of evidence, is that the expansion rate is happening faster and faster and faster and faster and faster, that the universe is actually blowing itself apart, and that the growth is actually exponential. That was completely unexpected. Okay, it was a complete experimental, observational, what the blank moment for the whole community. And the reason it's interesting from the standpoint of physics is when Einstein first wrote down the equations of general relativity, he did not know that the universe was expanding. And if you just take universe and put it on the table and say, here you go, general relativity, what's going to happen? It's going to go crump. It's just going to collapse under its own weight. And so what Einstein did was kind of put into the equations of general relativity by hand a sort of stiffness term that would counteract that collapse, an intrinsic sort of stiffness of space, if you like. And that was kind of a fudge at the time to at least make general relativity consistent with the observation that we're here. Okay? Then when astronomers discovered the universe was expanding, Einstein went, well, that was stupid. And so this term called the cosmological constant that he put into the equations, Einstein later called his biggest mistake. Because if he had not put that in, he would have said the universe must be expanding or collapsing. It's one or the other. And he would have made a prediction. So for a long time, the canonical wisdom was that there is no intrinsic funny part of general relativity, but quantum mechanics is a complicated thing. And if you take the idea of empty space quantum mechanically, the idea of the vacuum in classical physics is you just take out all the ropes and the pulleys and all the stupid things that you do in mechanics courses. And after you've taken everything out, what's left is the vacuum and there's nothing there. But quantum mechanically, the vacuum is the seething turmoil of particles and antiparticles being created and annihilating. And it's the seething foam of quantum mechanical fluctuations. And if you go to a theoretical physicist and say, hey, do me a favor, and in units that I can understand, please write down the gravitational impact on the universe of having all this energy of seething vacuum stuff going on. What's your prediction for what happens? And that leads to the most wrong prediction in all of theoretical physics by an incredible margin, which is that in relevant astronomer units, where the sort of natural density of the universe is of order 1, the answer is the impact of all this vacuum stuff is 10 to the 120th, right? The universe would have blown itself apart in the first nanosecond of its existence if that were true. But that didn't happen. We're sitting here in a universe where all those vacuum effects are completely subdominant. So the way that theoretical physicists dealt with that was to say, well, that's not right. True. There must be some mystical cancellation that to 120 significant figures, for every process, there's an anti-process, and this all just exactly balances out so that the net effect of all this vacuum fluctuation stuff is identically zero. Because otherwise, you're screwed, right? And for a long time, that was the prevailing point of view, that there are only two natural values for all this quantum fluctuation stuff. One is 10 to the 120th, which is manifestly not true, and the other is zero. And when we went out and measured it, it's 0.7. So where the hell did that come from? And that's why it's a crisis, is because it's incredibly hard to understand that number. And we don't currently know whether this accelerating expansion is a consequence of imperfect cancellation in quantum mechanics, or is it actually some little residual part of what Einstein wrote down in general relativity? And I'm kind of separating those two apart from each other because those are our two big theoretical paradigms, quantum field theory over here and general relativity over here. We do not currently have a quantum theory of gravity. And it's really interesting that this point of intellectual friction happens right at that dividing line between quantum mechanics and gravity. And to my mind, it's a big clue that we are missing something big in the picture here. And the now deceased Nobel Prize winner Steven Weinberg called this the bone in the throat of theoretical physics. It's just extremely hard to understand what's happening. And I believe we're living through an intellectual upheaval in physics that's every bit as profound as quantum mechanics was in the early part of the 1900s, but we're just in the really confused part of it. We haven't figured out, it's like we see the experimental manifestations of quantum mechanics, but we haven't put it all together yet. And it's been quite some time. The dark energy was discovered in 1998. And our predecessors figured out quantum mechanics in a shorter time interval than has already elapsed between the detection of dark energy. And what's unclear and a little bit sobering is, are we just going to stall out here and be in a sophisticated state of confusion for the next century? I mean, science has stalled in its history before, right? And in an attempt to avoid that dystopian outcome, my approach has been to say, okay, so we should test the foundations of gravity on every accessible length and energy scale and do every experiment we can think of, because maybe we're going to find some other anomaly. And then some really smart person is going to say, oh, I can explain it to you now. If I put this thing together with this thing, I can get to this idea. And now it all gets embedded in some larger intellectual fabric. So I think if the dark matter ends up being some new particle in the zoo of particles, that's interesting. That's cool. We will have solved a mystery. but it's not earth-shaking to have another particle. Neutrinos happened, quarks happened, electrons happened. Okay, so maybe there's some axion or some dark matter particle thing. That's cool. But I think the dark energy problem is more substantive. And I think a lot of people share that perspective.
So to bring this together, then we have pressing open questions in modern physics, as you were just describing. We don't want things to stall out. We have a great blueprint in your book for how the big projects happen, and you have chapters on everything from technical documentation to health and environmental considerations and so forth. You talk about budgeting and so. Talk a little bit about where we are on the funding of big projects in the physics community in 2025, because again, we profiled other sort of big project ideas, like we've had several guests on that are part of this bipartisan commission on biodefense, which envisions sort of a $100 billion Apollo project to prevent the next COVID from happening, and other initiatives like that. What is the big project that you would like to see in terms of some of these pressing open questions in 2025, and talk a little bit about what kind of sort of the funding of physics in this country is like today for big projects?
Yeah, so you didn't ask it this way, but let me, in a way, rephrase part of your question and
Please.
say, why the hell should taxpayer dollars go into building telescopes when we have poverty and all kinds of other challenges in the country writ large, right? I think that's a fair question to ask.
Sure.
And I think I have a multi-part answer. One is that the prosperity of the nation and the world has been driven in the last century by technical advances, by computers, by advances in life sciences, and all of those have their origin in basic research. And the problem is, it's really hard to tell early on which thing is going to be highly impactful, right? The World Wide Web got its start when particle physicists tried to find a way to communicate information to each other electronically over this evolving internet that was built at the time. And that led to all the search engines and everything else that we all use every day. Nobody knew that was going to happen when they started funding accelerator physics. And the sort of linkage from early basic science into highly impactful technologies is so unpredictable that we need to lay the seeds in a lot of places and then nourish the things that really sprout. Second, it's the training ground for the people who go on and push those things forward. It's people that make things happen, people with good ideas who are capable. And those people grow largely in their early years in academic research experiences, where in some ways the price for failure is low.
Mm-hmm.
The consequence of failure is low, and they get experience early on in, ever increasing levels of responsibility and accountability. So there's the human capital part, there's the lay the seed for technology part, and then there's the sort of human aspiration part of it. And that is people like me are privileged to be our society's ambassadors at the intellectual frontier. And we are a species that craves knowledge, understanding, and adventure. And we break that path and try to share that experience broadly. And in that respect, in particular, I think astronomy is often the sort of gateway drug for the sciences. I think young children, telescopes and dinosaurs, right? Get hooked on doing science stuff early. And the projects that we're involved in now have a large effort of K through 12 outreach to really capitalize on dragging kids to the intellectual frontier and saying, look, you can download images off this telescope. You can find asteroids. You can do this really cool stuff. So that's another, I think, important societal consequence of this. So at the top level of the government, the federal budget allocates funding across different science agencies. That then gets awarded to projects on the basis of peer-reviewed competition in My particular subfield at the National Science Foundation that funds a lot of observational cosmology, the success rate for proposals is around 15 to 18%. So it's a very heavily oversubscribed resource. It's highly competitive. And only the best projects win out and
Mhm.
succeed in securing funding. Um, the challenge that we face with an ever increasing federal deficit and the fact that about the only place to trim the federal budget is in discretionary funding makes me quite fearful about the long-term prospects of federal funding for science in the nation. But for the reason that I said at the very beginning, which is that basic research in the science lays the seeds for economic prosperity in the long run, I think it's essential that we continue to do so.
With that, I want to take a short tangential move here. As I said mentioned in the bio of the show, one of your roles has been as a member of the Jason Advisory Committee of quite elite scientists that advises the United States government on a variety of science and technology matters, and of course, a lot of the output of this committee are classified. I'll only ask you about the stuff that I was able to find declassified, but was just interested if you could say a couple words about at first how you were originally selected for the Jason committee. What meetings were, I mean, I know there's a lot of theoretical physicists there, but you're also there with biologists and oceanographers and so forth. Love to hear any anecdotes about sort of when you're discussing the most important things for the country in terms of science and tech, how some of those debates go. And then just, I guess, when I first hear about the Jason Committee, I always think, oh, you're in a secret bunker somewhere underneath the bunker, underneath the Pentagon. But no, I think most of the meetings happen to the MITRE Corporation. Any interest, were you fed well? Any interesting stories? Take that one in any direction you want. Love to hear about what you can talk about.
Yeah, so I think my version of the history is that the Jason Group had its origins after the Second World War and the Manhattan Project, where the physicists basically went to the government and said, hey, we helped you win that war. We think it's in the interest of the nation for there to be an ongoing engagement between the government and the physics community that are willing to contribute in the national security arena. And that led in the 50s to the establishment of this group, which is a sort of self-selected group of primarily academic scientists and engineers who choose to invest a fair amount of their time, effort, and energy in trying to help the government struggle through the sort of overlap between technical issues, national security, and trying to do the right thing. Uh, the the group picks its own members. And so I got a phone call one day when I was at the University of Washington that said, hey, I'm so and so. You probably don't know about this Jason group, but we'd be interested in having you come and think about possibly joining. And I went in with some amount of trepidation and apprehension. Like, is this the right match for me? Is this going to work? And, I don't want to build nuclear weapons. And the more I learned about it, the more I thought, I think it is in the nation's interest to have a disinterested, nonpartisan, impartial group of cleared individuals to give some amount of peer review and scrutiny to projects that the government undertakes and spends a lot of money on, right? So the group tends to get together in California for 5 or 6 weeks over the course of the summer and put your head down. And the easiest way I can describe it is the product of this group is to write reports. And each of those reports, when it's a good one, is kind of like a PhD dissertation written over the course of a summer in partnership with two or three other really smart people. You do a really deep dive and sort of lay out the foundational technical and scientific issues, make recommendations to the government about a path forward. Sometimes the outcome is to say, this would be a waste of taxpayer dollars. And I think some of the most impactful Jason reports that I've been involved in have actually said, no, don't go spend billions of dollars on this. It's not a good thing. And one of those alone pays for the entire JSON program for a century, right? If you sort of think about the cost benefit trade
Yeah.
for the taxpayer. And it's really quite interesting. Projects range from privacy issues for the Census Bureau and how to deal with identifiable information and trying to execute the national census, a variety of things for lots of different federal agencies. And there is a huge opportunity cost for those of us who are academic scientists, because in a way, the summer is the time period during which you can really put your head down and get your research done. And taking time away from that and contributing it to this does extract a significant professional opportunity cost. But I've been doing it for 20 plus years, and um, I have no regrets. I think, not every single Jason study is hugely impactful. Many of them just sink without a trace and aren't acted on. If hard as this may to believe, the government does not always take our advice to heart. But but then there are a handful of studies that are highly impactful.
Mhm.
And one that I'll give you an example of is when the nation stopped doing underground nuclear testing,
Yeah.
there was a highly influential Jason report that sort of said, yeah, you don't need to do this anymore. We think we understand how these things work. And that led to, you know, unratified but compliance with the test ban treaty in this country.
Yeah. Yeah. Talking about I took a look at several of those, or the declassified ones that are available. Actually, these are in the Federation of American Scientists database, and two that stood out to me just because they're so extremely timely. And the one was in 2000, which is entitled "Data Mining in the Human Genome," and the other one in 2004, "Computational Challenges in Medical Imaging." Both resonate with everything that's happening right now with AI and all these interesting tools about how we got all this great data, but we still need to better understand it. That's one thing, but the other thing that came to mind is we're seeing such a reconnection, if you would, between the world now of biology and physics, from everything from optogenetics to some of the stuff that's happening with the quantum computing and drug discovery. Love to get your perspective just on the bio side of things, and about where you areas of interest in terms of this biophysics reconnection. And again, these two reports, 20 some odd years ago, are quite pertinent to what's happening right now.
Yeah, so one of the things I'm proudest of professionally is of the students and postdocs that I've trained, a good half dozen or so transitioned into gene sequencing technology and applications, right?
Yeah.
So I'm really proud of the fact that they had the sort of breadth of perspective to think it was a viable thing to make that big of a professional switch, and that they had the technical wherewithal to make contributions in that arena, right? Which is sort of photon-starved optical gene sequencing technology,
Yeah.
which has a lot of overlap with photon-starved astronomy and detectors and optics and all that kind of stuff.
Yeah.
So I think there is a lot of crossover. The the places where I think there's a lot of direct overlap include machine learning and AI assisted analysis of imagery writ large, right? Astronomers take pictures of the sky. You've read all the papers about radiology applications of AI
Yep.
classification problem. I
Yep.
think that's all a common emerging explosion of technology and its applications across a wide range. And a lot of scientific data collection is imaging. So I think that's a really interesting and fruitful arena. I think broadly speaking, large language models and generative AI is going to completely change the way that we interact with data, where now we make natural language queries of information and that's only going to accelerate. And I think that's a case where a combination of domain level expertise and competence with those tools is what's going to lead to progress. I am a little fearful about people reaching for the cotton candy of asking ChatGPT questions that they don't know a lot about and getting answers back that aren't correct.
Yeah.
But I think that as long as that domain foundation is there, I think that's a super powerful combination that transcends subfield boundaries. I think on the quantum computing side that you mentioned, that's really interesting. And the sort of subset of problems of interest that are amenable to quantum computing is actually fairly narrow. And the whole drug discovery, synthetic compounds, try to predict characteristics and properties of macromolecules, I think is a place where there could well be some really fruitful applications of quantum computing as one of the early things that we see. But I'm a little guarded on that, right? I mean, like let's see how that all goes. There are some early examples that are promising, but let's see how it turns out.
Yeah, yeah. But I profiled a few of those programs, and to the extent I understand anything about I'll call it quantum light, some of these first generation or whatever generation machinery we're on. Yeah, it's going to be interesting to see where it all goes and how it pans out in terms of that industry. Chris, Chris, moving from bio to nuclear, you 2012 in the book The Nuclear Enterprise, you authored the chapter. It's entitled "The Interplay Between Civilian and Military Nuclear Risk Assessment and Sobering Lessons from Fukushima and the Space Shuttle." And again, interesting times where we're on one hand we're profiling on the show the sort of the next generation tools, the molten salt reactors, the small modular reactors, and then we got an active war going on where people are shelling each other around active nuclear power plants. And again, love to get your perspective on how you think about all things sort of dual use nuclear in 2025. And then at the same time, I ran into this other really cool paper that you wrote on. It was entitled "How to Detect a Nuclear Test on Your iPhone," and this really interesting citizen science app. It's funny because I was joined just last year by Dr. Robert Floyd from the Comprehensive Nuclear Test Ban Treaty Organization, talking about all their high tech sensors and all the stuff they have, listening in on whatever North Korea is doing and all that. Love to get your perspective on sort of other cool applications of citizen science as it pertains to the nuclear enterprise.
I think you're the only person who's read all those things. So a lot of that work came out of the time that I spent at Hoover with George Shultz and Sid Drell, sort of thinking about verification protocols and forward-looking at technology and its application broadly. And I guess there are two separate points here. One is, how many times do you open the paper and read about a once-in-a-lifetime thing that happened?
Yeah.
Over and over and over again. So how are these statistics calculated? And how meaningful are they? And to what extent should we base policy and investment decisions on those risk assessments? And what error bars do we attach to those risk assessments, right? I'll give you a really contemporary example, right? So the lead industrialists in generative AI, I've heard say that there's a something like 20 to 30% chance of generative AI evolving to be a civilization-ending technology. Think about that for a second. A what? 20% chance that ChatGPT 28 is going to turn into Skynet and obliterate mankind and turn into our robot overlord? Like, really? That's your ranking? If you were to ask me what risk would I think acceptable for this technology to move forward? I would pick like 10 to the minus 9. Okay. And they're saying 20%. Where did that number come from? And is that just hype to get in the newspaper? Or do these guys really believe that there's a one chance in five that this technology is going to end life on the planet as we know it? Right? And if so, what the hell? Why are we moving forward with this? And that whole space of risk assessment, risk perception, and policy decisions is this really complicated combination of human psychology, quantitative assessment of risk, actuarial statistics, and whatever, right? People who are driving down the highway saying, I'm worried about getting on the airplane, have it exactly backwards, as you well know, right? So that that first paper that you mentioned was really just sort of an exploration of looking back and triggered in part by Fukushima at the time, what is the occurrence rate of these things that were, when the project was embarked upon, were deemed to be inconsequentially small risk, right? And
Right.
there are lots of examples of projects that were undertaken on that basis where that risk assessment turned out to be not accurate for a variety of reasons. And just trying to highlight that the complexity of making those decisions was, I think, the point of that chapter. On the iPhone verification of arms control and other treaties, I do think there's an interesting question about how ubiquitous high-end technology can be used by the public in the sense of sort of NGOs and crowdsourcing of information to assess compliance with societal expectations, right? Broadly speaking, you know, I think our current model is we delegate to the EPA and other federal agencies monitoring water quality and air quality and doing enforcement, all that kind of stuff. Well, you can put sensors in your house in the sort of Internet of Things mindset that
Mm-hmm.
can monitor a lot of things of interest. You get chemical contaminants or microplastics or whatever, right? Now, does your current cell phone contain all the sensors to do all of those things? Well, not quite, but look at what they have in some smartwatches with physiological monitoring and the like. You can put a lot of sensing technology and distribute it widely. Interesting policy decisions there. How do you pick? How do you disseminate? How are the data available? Who aggregates the information? Is it only going to be big companies, or do we somehow empower citizens more broadly to take things into their own hands and perhaps introduce a level of governmental accountability that we weren't able to do previously? I think those are all interesting questions to ask and think about,
Mm-hmm. Mm-hmm.
to which I don't have any.
Um, Again, no, I appreciate giving your thoughts to all these, and again, all extremely important insight in terms of where science continues to need to go and to solve these questions. And just ask you one other thing, Chris. While we're on the topic, because you mentioned your work with George Shultz and another I know we're not part of the Open Skies Treaty anymore, but you wrote this piece about a decade ago on sort of the importance of the Open Skies Treaty, not just in terms of nuclear verification, but the other things that this could potentially give us. And you're pointing out issues in terms about mapping greenhouse gas emissions and so forth. And then I also noticed you have been involved in work in terms of well, let's call it generally remote sensing, things in terms of looking at methane seepage on the East Siberian Arctic Shelf. Again, I'd love to get your top line on sort of um, the importance of obviously remote sensing tools, but again, any interesting applications that you would like to see, big program or citizen science, in this particular area? Because again, another, I'm not worried about Skynet and ChatGPT. I am worried about some of these other things. And again, while we have you today, we'll love to get your perspective on this per 2025 as you have studied it as well. Not just looking at the cosmos, but looking down at other important things that are happening on this planet.
Yeah, so that's been a really interesting thing to watch evolve. I mean, for a long time, the ability to put a camera in orbit and point it at the Earth and take pictures of things of interest was the domain of spy satellites. And, the great powers embarked on that for a long time, for decades. And there's been this complete transition in turnover to where now commercial entities and NGOs, non-governmental organizations, are flying flotillas of satellites in low Earth orbit.
Yeah.
Some of them equipped with camera systems, some of them equipped with synthetic radar, some of them equipped with radar receivers that can receive the beacons from ships and look at illicit fishing activity, right? So there's just an explosion of data access that we didn't have before. And thinking about how to bring that capability to bear on public policy issues and making the most of it, I would say broadly, I think is a really interesting arena. And I salute a number of companies that were incorporated as public benefit corporations that are doing a lot of this work, where not only do they have a fiduciary responsibility to their stockholders, but as part of their charter, have a sort of do public good responsibility and are acting on it, right? So a lot of those companies are making data accessible for a variety of applications, right? Some of them, a lot of these pictures that you see in the newspaper of war in Ukraine, of consequences of natural disasters, those are all acquired by those systems. And um, I think that's only going to go faster and faster and faster. The thing to worry about and the downside here is that we are almost already at the point where the number of objects in low Earth orbit presents a hazard of collisions that leads to a runaway situation of contaminating the orbital space above the Earth. And that is all so unregulated that it's a lot like the Wild West. Satellite operators don't really need to get much in terms of licensing other than radio frequencies, and they just put them where they want. And a lot of them are flying them way too high for our taste. And they just don't fall out of orbit. If you put them up at 500 kilometers, their orbital lifetime is essentially indefinite. And if we lose control, they will eventually run into each other, produce debris that runs into other ones that makes more debris, that makes more debris. And before you know it, we've made trash out of outer space. So that's something that I think deserves a significant amount of attention.
Chris, what's coming up for 2025? What what do you want to see as the next sort of frontier work happening in physics and in astronomy and observational cosmology? If I was to give you $1 trillion today and fund the Chris Stubbs Institute of Frontier Sciences or whatever, what do you want to see happening? What do you want to see happen next? Take us into the future.
Well, that's a question for which I am unprepared. Um, 2025 will see the transition of the telescope behind me from construction into operations. And that's a cool thing. I'm spending my
Yep.
time on that. That's my near-term focus. I think the broad areas of drug discovery, therapeutics, and cost-effective generation of molecules that help us defeat disease. I think, the sort of computational, not quantum computing, but sort of AI-empowered efficiency of drug discovery,
Mhm.
I think is still in the early days. And I'm optimistic that that will provide dividends in the long run. I think the government just announced a huge investment in computational platforms for the development of AI. I think it'll be very interesting to, yeah, I guess I would fund a major research institute to ask the question, not what can generative AI do, but what should we do with it?
Mm.
How do we manage that technology in a regulatory sense for the common good and to make people's lives better and not worse? And if you look at social media, there's a really good example of maybe not doing such a great job in an analogous situation. Um, I clearly fund every single astronomer who asked for money to do whatever they thought was a cool thing to do.
Me too. No, really, really awesome discussion, because I just really enjoyed, learning and hearing about your entire journey, the the breadth of topics that you focused on over the years beyond sort of the core disciplines. It's just, it's quite interesting, and I really wish you and your team the best with all this as you continue to move the programs forward. Really exciting work. Again, for everybody that is going to be listening to this episode of our show across the various podcast networks, or who'll be watching with us on the YouTube channel, again, you've been spending time with Dr. Christopher Stubbs, Samuel C. Monka Professor of Physics and Astronomy, Harvard University. Pick up a copy of his book, Going Big, The Scientist's Guide to Large Projects and Collaborations, which really is a very nice and concise compendium of all the important skills that scientists need to make these big projects reality. Chris, again, I want to thank you for taking the time out of your schedule today. Obviously, thank you for everything you've been doing there and in your lab. And as we like to say on our show, thanks for helping to create a better tomorrow via the type of work you're involved in. Really an awesome story. And I really wish you the team the best with it all.
Thank you. It's been great talking to you.
Great having you.